Key technologies for innovative decarbonized heating and cooling system. My name is Prof Zhao, is a fellow for Royal Academy of Engineering, fellow for European Academy of Science, and director of Center for Sustainable Energy Technology at the University of Hull. So my talk today comprises three parts: brief of CSAT at the university, and a brief novel solar-driven heat pump heating system, and finally introduce a novel dew-point cooling system. Talking about CSAT. CSAT is a specialist research cluster dedicated for energy research. It covers the theme of renewable energy, includes solar, earth, wind, and biomass, energy efficiency, address issue of heat pipe, heat pump, and CHP. And the third theme is sustainable building service, which address heating, cooling, lighting, ventilation, and air quality. And smart energy system, which address intelligent monitoring, control management, big data, cloud computing, and machine learning. And also we address some energy storage technologies, particularly thermal storage. And also we cover issue of distributed energy system. So talking about CSAT team. CSAT team is vary time by time, depend on budget availability, depend on project, and depend on student number. Currently, we have around 15 people working on different projects, including 6 research grad. So summarize of our achievement. Up to date, we have complete about 68 research projects with funding value of about 28 million pounds. We have 6 ongoing projects worth of 1.7 million pounds. We published more than 330 papers. We have 40 patents. We have published 8 books, and we have supervised 31 postdoc research fellow and 41 PhD student. We have involved more than 40 engineering consultation projects. So this is our ongoing project. You can see from the list we have 2 EPSSC project, 1 Innovate UK project, 1 Royal Society project, 1 EU project, and 1 UK HIP project. In total, we have a budget value of about 1.7 million. So University Hull publicized the sustainability report in the end of 2023, which indicate our CSAT research budget as well as research impact ranked top position in the university. So we achieve a world-class standard in the following 4 topics, namely, number 1, super performance dew-point cooling system, which have a COP of 15.2.5, represent world highest standard in energy efficiency. Number 2, have developed a hybrid solar heat and power system that enable for utilization of solar spectrum and enhanced energy efficiency. Number 3, we have developed a dual source heat pump employee vapor injection and entropy increase compression. Also, we have developed a kind of heat pump technology which employ the liquid upside feeding and gas liquid separation mechanism. This is for area we addressed and achieved some success in the past year. Now we move on to the part 2. We're talking about a novel solar-driven heat pump heating system, which cover 4 different parts: background information, technology description, thermodynamic performance, as well as system demonstration. So talking about background, as we know, UK, like most the country in the world, is all the way toward to net zero. It's set of the target that indicate by 2015 UK would reach a net zero in carbon emission. However, currently, heating market is not very optimistic. Only about 2% of heating system is considered as low carbon. Majority of heating systems is still dominated by gas boiler, which need to retrofit and replaced by so-called low carbon heating system. Heat pump is as a mature and energy efficient heating device which utilize electricity because the majority of electricity is renewable generated. In that case, heat pump would be a feasible pathway toward net zero. From now to 2030, they would have more than 2.5 million heat pump to be installed in the new house. Uh, for the public infrastructure and industry infrastructure, we assume that they would have more and more heat pump applied in next decade or a couple of decades. So we're talking about solar heat pump. Solar heat pump is a kind of a combination of the solar collector and the heat pump. This kind of system or technology could be applied to different climatic conditions. However, if this technology applied to the mid and high latitude climatic condition like UK, it presents a number of inherent difficulty and disadvantage. Number one, solar collector array have a very, very low thermal efficiency in the winter. Normally, it would be less than 10% because of cold climatic, cold environment, and significant heat loss and reduced heat collection efficiency. Also, COP of heat pump is very low. Our testing show majority of heat pump, air source heat pump, have a COP of only 2 or even less than 2, which is not quite economic and economically feasible. And the contribution of solar energy to the whole heating demand is quite small. Most time is less than 10%, sometimes only 5%, particularly during the winter. It's just a big issue. More importantly, you got a problem of frosting because you got evaporator. During the winter operation, evaporator would be frosted. In that case, we need a defrosting treatment, which consumes significant amount of electric energy. Statistics show that about more than 20% electric energy is used for defrosting of heat pump, which is a significant amount of energy waste. To address this technology challenge, we have developed a low carbon heating system for public building. This project get funding from the UK government, Department of Business, Energy and Industry Strategy, with a funding value of more than 2 million. Project is led by University of Hull, involved the 3 partners, namely NPS, PCM, and the Hull City Council. Look at the schematic of the system, which comprise 3 major parts. Part 1 is the heat pump, we call it double source heat pump, use vapor injection, increase compressor, which can recover heat from ventilation air as well as ambient air. And that way, we would be able to uh, raise its COP to 30% more than the traditional air source heat pump. Second part of the system is the solar collector array, solar panel array. We use a normal connection miner or fluid flow miner, which is a multiple through flowing flow mode, which can average temperature difference, temperature distribution of different solar panel, reduce the heat loss of the solar panel at the end of the array, and increase its overall solar thermal efficiency. Furthermore, because of the horizontal flow with least that flow direction change, it can significantly increase the energy efficiency ratio. Energy efficiency ratio would be doubled than the traditional one-to-one seriously connected solar panel array. Third part of the system, we call it fast responsive heat storage heat change tag, which can provide heating fastly and quickly in the morning when solar become available. We don't need to wait a long time. Now we can deliver heating in about 20 minutes when sun arise. That is a three major part of the system. Of course, we got internet-based control. So look at the heat pump. We use the double evaporate system. And first evaporator, which is called middle pressure evaporator, which can recover heat from exhaust air of the building. And after this evaporator, exhaust air would mix up with ambient air in the mixed chamber, then into the second evaporator, which is used to recover heat from the mixed air, both ambient air and exhaust air. In that way, we would be able to recover heat from both exhaust air and ambient air twice, which can minimize ventilation heat loss and maximize heat recovery from the two energy sources. And secondly, defrosting of the heat pump would no longer use electric energy. Instead, it uses ventilation air. In that way, we can reduce electric energy consumption in the heat pump operation. So this is a design drawing of the heat pump. You can see you got a medium pressure evaporator, you got air mix chamber, and you got second evaporator, and at the opposite side you got air discharging as well as vapor injection and INSP increasing compression. Look at the test room. This is a test room that can simulate the room space temperature, which is greater than 20 degrees Celsius. It also can simulate ambient temperature, which is 0 degree, could be minus. And we can use this heat pump to generate hot water, which is greater than 35 degrees Celsius. It could be 45, 40, 15, 55, 65, and 75. Maximal temperature we can generate from this heat pump is about 75 degrees Celsius, which is very, very beneficial compared to traditional air source heat pump, because a traditional air source heat pump can only generate hot water of 15 degrees Celsius. It's not high enough for some kind of heating service. So look at the schematic of the heat pump. You got a condenser. After condenser, you got the refrigerator that is delivered into the two evaporator, into the two evaporator. First the refrigerator stream goes through the medium pressure evaporator, in which it recovers heat from exhaust air. After the evaporator, it is go to the internal heat exchanger, in which it take heat recovery. It could be used to cool the second refrigerant flow and cool the second refrigerant flow down to the subcooling state. And afterward, this kind of secondary refrigerant flow goes through the secondary evaporator to recover heat from the mixed air. Two parts of refrigerant would meet at the compressor. In the compressor, we got high pressure refrigerator and a low pressure refrigerator. Two refrigerant stream would induct induce one after another. In that way, we would be able to create kind of injection effect, thus reduce the power input of the compressor. After the compression, then the refrigerant go to the condenser where it is release heat and be fully condensed. Yeah, that is a cycle. So this kind of cycle make use the vapor injection compressor for ventilation heat recovery, lead to increase the COP, and secondly, we use the ventilation air to defrost heat pump. In that way, you will be able to reduce electric energy consumption of the heat pump. So compared to traditional exhaust air heat pump, which have only one evaporator, our new heat pump, which is vapor injection, increase compression with the two evaporator, which can recover more heat from ventilation air. Recovery heat will be almost doubled, and the temperature reduction potential almost doubled. In that case, you got much large heat recovery and heat supply, and the heat recovery rate would be significantly increased. We also use kind of a new solar panel, which is a micro-channel flat plate panel. We try to make a new configuration which is physically separated into three parts: low part, medium part, and the up part. We got three inlet and three outlet. In that way, we would allow the solar fluid go through the low part of the panel, then come out the first panel, enter into second, third, fourth, and to the end of the panel, possibly 10, possibly 20. And in that case, make a horizontal movement. At the end of the panel, fluid would turn around, travel into the medium part of the panel, then fluid would flow backward from the end to the beginning. In the beginning, it would flow again, uh, turn right, go to the up part of the panel, then make another throughout flow. In that case, you can make three throughout flowing, and by doing so, you would be able to average temperature of the first panel, second panel, and the end panel. So temperature uh, of the panel surface almost the same. This kind of fluid flow will be able to reduce the temperature of the end panel, reduce its heat loss, increase the efficiency of the end panel as well as the overall panel array. As a result, overall solar thermal efficiency of the panel array will be increased. And more importantly, because of the horizontal flow with a little direct changer, so flow resistance would be minimized compared to traditional seriously connected panel array. So in that way, you will be able to get much higher EER value. So this is a configuration of the microchannel solar panel. We use the microchannel to make the panel, which have a dimension of the 2.5 millimeter and 1.5 millimeter. It is a millimeter scale geometry that can accelerate the flow speed, increase convective heat transfer coefficient. In addition, we got corrugated geometry on the inner surface of the microchannel, which disrupt the laminar flow layer, create turbulent flow condition, which can further increase the convective heat transfer coefficient between the surrounding and the fluid in the panel. So that would lead to increased heat transfer and increased thermal efficiency. So in our first set of experiment, you have a panel which is made three inlet, three outlet. In that case, you would be able to create three throughout flowing, which travel horizontally across the panel array from beginning to end, from end to beginning, and finally from beginning to end. That is the way of the fluid flow and the connection, which can significantly increase the efficiency and reduce the flow resistance. So first set of experiment, we use 8 panel, which a solar area of 16 square meter, which is connected in the way of multiple through flowing. And we try to pass the cold fluid from the downside of solar panel, which absorb heat from the panel, then become gradually hot, and the hot fluid then go upward to the middle part of the panel, and finally travel across the up part of the panel. In that way, panel temperature in the beginning to end would be almost uniform, which can prevent overheating of the panel at the end of the array, because the cold fluid would enter into low part of the panel. At the low part of panel surface, you got cold surface, you got low temperature, and high part of panel, you got high temperature. So temperature profile of the panel would be shown in the left side which is something cold on the low part and hot in the upper part. In this kind of temperature profile can somehow refrain the convective flowing around panel because the low part of panel is cold, upper part of panel is hot, which can somehow restrain the convective flow, reduce the convective heat loss to surrounding. And the third part of a system, we use kind of fast responsive heat storage heat changer. We got a kind of a tank, a big water tank. We separate the water tank into two parts. At the low part is a heat changer part, and the upper part it is heat storage part. Its low part we try to keep a small volume, for example, 20 liter or 30 liter, which limited the volume of the heat transfer fluid, which allow the heat could be quickly absorbed by heat transfer fluid, and the temperature of heat transfer fluid quickly arise to the required temperature, which can be quickly delivered into the service room in about 10 minutes, 20 minutes, where solar radiation is become available. At noon or sometime sunny timing, for example, 12 o'clock, 1 o'clock, 2 o'clock, where the service room is hot enough. In that case, we don't need provide heating. During that time, heat transfer fluid would break through the single way valve in the separation panel. This kind of heat transfer fluid would go upward, mixed with the water in the heat storage tank, have some amount of heat stored in the upside tank. So stored heat could be used for the evening or even long-term use. For example, 12 o'clock evening, it's still available for heating because a certain amount of heat storage available in the tank. So we use the internet-based control mechanism that could control the heat pump, control the solar panel, control the flow path of the heating fluid, whether or not it's come across heat transfer chamber or go straight to the service room. And of course, all of the control is based on the room temperature. Everything's controlled by room temperature. We can switch off heat pump, switch off solar panel. We can choose flow path, whether or not it come across the heat storage heat change, or it can go straight to the other flow heating. This is a multiple option that is controlled automatically by a dedicated control mechanism. So look at the storage tank. This is very big, more than 1.5 cubic meter or more than 1.2 cubic meter. We separate this tank into two parts, and the low part is just have a small volume used to store heat transfer fluid, and up part is a large volume which is used to store heat storage fluid. So compared to traditional heat storage, heat change tank, which have a big volume, need a lot of time to heat up the tank water. In that case, we need a lot of time to supply heater to service room. For our new heat storage heat change tank, you got quite small heat transfer fluid chamber. In that case, heat transfer fluid could be quickly heated and delivered into room space whenever needed without wait for a long period of time. So that is a system profile. Now we look at the thermodynamic performance of the system. First of all, we made a dedicated simulation heat pump. We simulate our double source vapor injection heat pump. We also simulate conventional vapor injection heat pump and air source heat pump. We make a parallel comparison between these three heat pumps. To facilitate simulation, we made a following assumption. First of all, compression efficiency is assumed to be 80%. Minimum temperature difference between refrigerate and surrounding would be about 5 degrees Celsius. We assume refrigerate would be R140A and air temperature drop in low pressure evaporator would be 5 degrees Celsius. So with this assumption, we made a delegated simulation. The figure in the left and the right side show the performance of the heat pump. Left side, you got COP against the ambient temperature. You can see three heat pump. Our double source vapor injection heat pump got the highest COP, and air source heat pump got lowest COP. At low ambient temperature, this kind of increase rate would be higher than high ambient temperature. When you increase ambient temperature, COP would be increased almost linearly. Right side figure shows COP against the condensation temperature. Again, our double source vapor injection heat pump got highest COP. When you increase condensation temperature, COP will be decreased. And simulations show that double source vapor injection heat pump have a high COP, which is 23.2% higher than the conventional air source heat pump. At a low ambient temperature, this kind of increase rate would be higher. We also look at the COP against injection temperature and the heat capacity against injection temperature, because we got two refrigerant stream flow, and you got injection temperature, which have optimum value at condensation temperature of 45 degrees Celsius. Optimum injection temperature would be about 5 degrees Celsius. At this temperature, COP reach maximal. You can see. Also, if you increase injection temperature, heat capacity heat pump will be decreased. So apart from energy performance simulation, we also look at energy loss, which is called exit loss. So we look at exit loss and the different part of heat pump and work out its breakdown of exit loss. Simulations show that highest exit loss take place at compression, followed by condenser, LP evaporator, then we got MP short valve, then you got internal heat changer, then you got MP evaporator, as well as MP evaporator. You can see this is a breakdown of exit loss in the right side. So apart from simulation, we did delegated measurement of the operational performance of heat pump at a real-time operational condition. we installed the temperature sensor, pressure gauge, and flow meter in the key point of the heat pump system. Inlet, outlet of evaporator, compressor, internal exchanger, condenser, as well as heating coil. So we get the measurement date, compare it to simulation. We work out the correlation between COP and ambient temperature, as well as ventilation flow rate. From the figure in the right side, you can see COP increase with increase of ambient temperature. When you increase the ventilation flow rate, COP will be increased. So at the winter operational condition, heat pump got a COP of 3 to 4.5, which is 30% higher than that of conventional heat pump at the same operational condition. So we test the performance heat pump day by day during the winter. These two figures show the operational performance of heat pump at two different winter days. You can see the heat output against ambient temperature. You can see increased ambient temperature, heat output will be increased. Increased ventilation flow rate, heat output would be increased. At the two different operational day, the performance that show the similar trend of variation. We found at the winter operation, we normally can get even higher heat output, which is about 6 to 11 kilowatt, higher than the nominal heat output, which is 3 to 5. So we indicate our heat pump performance even better than the operational condition. So obviously, heat output increase with the increased ambient temperature and with the increase of mass flow rate of exhaust air. Another distinguished advantage is the reduced defrost time. For the traditional air source heat pump, which use electric energy to defrost, which need longer time for defrosting, we consume a significant amount of electric energy. However, if we use the ventilation air to defrost heat pump, its defrosting time would be significantly reduced. Our experiments show at the -5 degrees Celsius, defrost timing will be less than 10% than the total operation time of the heat pump, which can save significant amount of energy and put a heat pump in the operational condition, minimize its energy waste. We also made parallel comparison between conventional air source heat pump, exhaust air heat pump, traditional weapon injection heat pump, and our heat pump. So this kind of table and figure show its comparison result. In terms of power demand, our heat pump got lowest power demand because of high COP. In terms of capital cost, our heat pump have a higher initial cost because a little bit complex structure, but this high cost could be recovered from reduced electric bill in about 1 to 2 years timing. In terms of operational cost, our heat pump got lowest operational cost because of reduced the electric energy consumption and reduced the electric bill. In terms of requirement of auxiliary heating, our heat pump got lowest requirement, where traditional system got higher requirement because sometimes a heat pump is not enough. We need auxiliary heating. So look at the solar panel array, because we install kind of a solar panel array which could be used in daytime. In that case, you can reduce the operational time of heat pump and maximize use of solar thermal energy. So we try to configure 8 panel. We test the performance of the panel and try to install kind of a temperature sensor, flow meter at a different point of the panel array, inlet and outlet. In total, we have the 25 point, which installed the temperature sensor and the flow meter. We call 25 point maximum point. So we test the performance of solar panel array at the real-time operational condition from morning to afternoon. So this figure shows the solar radiation and ambient temperature variation in the daytime. So we got a temperature variation for different pipe section. We got pipe 1 from 1 to 2, pipe 2, pipe 3, pipe 16. And from point 1 to point 9, which is the pathway for the first throughout flowing. From point 9 to point 17 is the second throughout flowing. And from the point 17 to point 25, it is the third throughout flowing. You can see it's a solar efficiency for different throughout flow. And also we got average solar thermal efficiency for this panel array, which is in red line. Results show that during the daytime operational condition, the solar panel array can achieve solar thermal efficiency of 78% at panel temperature of 16 to 17 degrees Celsius, which is higher than that of a traditional one-to-one connection solar panel array. This is our real-time measurement result. Look at the EER. EER value is the ratio of heat output to power input for pump. You can say because of the reduced flow direction change, we can achieve a significant high EER value, which is about 400. A traditional one-to-one connection solar panel array got a EER value of only 200. We almost double EER value for the solar panel array. Look at the heat storage tank. Our new fast responsive heat storage tank can quickly heat up the fluid and reach a required heating temperature of 40 degrees Celsius in about 20 to 30 minutes. A traditional heat storage tank need about 3 hours from 8 o'clock to 11:30 or 12 o'clock. So it's a lot of time waiting, which is a kind of energy waste. So 20 minutes against 135 minutes, which is a totally different. So again, look at operational performance at a different operational day in the winter. It's just all similar trade-off variation. This is a performance. And now we look at system demonstration. We have this kind of system demonstrated in different locations. Our first demonstration will be in China, in Shanxi province, we installed this kind of system in the village house, in which we use 18 panels. We use one heat pump and one 1.5 cubic meter of storage tank, which could be used to heat a village house for the whole winter. That is our first demonstration project. Then we test the performance of the system in Guangdong 5-star. We got 8 panel. We got 5 kilowatt heat pump. We got 1.6 cubic meter storage tank. We tested performance, and for the whole winter, we got a good result. Then we tried to copy this technology and install this technology into applied science building of University of Hull. You can see we got 8 panel, we got heat pump, we got fast responsive heat storage, heat change that being used in the university building for heating up the classroom and being running for more than 5 years. We also applied this technology into a whole city library, which is a building located in the city center of the Hull. We try to use 20 kilowatt of system to heating up the workshop of 800 cubic meter workshop. So we use a 20 kilowatt of double source heat pump. We use 32 solar panel, which are connected in multiple throughout flowing way. We make a dedicated internet-based control. We can control the system, control heat pump, control solar panel, control the storage, heat change, control the flow bus. All of these things being made on internet. We can do the real-time monitor. We can do real-time control and adjustment, and we can implement whatever demand from user and try to justify the operational way of the system. And we monitor the system from home and use the internet. Recent years, we tried to use this technology in the whole city council house. We install 8 kilowatt of heat pump and 4 PV panel into the solar into the whole city council house. What our strategy is make zero bill heating. We use the solar photovoltaic to generate electricity, which could be sold to the grid. In winter, we try to buy electricity from grid to driven heat pump. Our strategy is make zero bill because our sale price of PV electricity try to be equalized to be a purchase price of electricity for heat pump. In that way, we will be able to create zero bill heating for the council house. So that is a schematic drawing of the council house zero bill heating. That is something we have done recent years. So last part of this lecture, I would like show another technology, which is called dew point cooling technology. This is technology being investigated by our group for more than 15 years. We have generate 3 generations of dew point cooler. Our latest generation of dew point cooler achieved COP of 15.2.5, which we think is the highest standard in energy efficiency compared to parallel technology available in market, because the COP is 15.2.5. where traditional commercial technology have a COP of 20 or 25. We almost double this kind of energy efficiency. So technology comprises a number of innovative aspects. We try to brief this kind of innovation. Our first innovation is kind of irregular heat exchange plate. On the inlet and outlet of the heat exchange plate, we use flat surface that would facilitate air and water distribution. However, on the main heat transfer uh, section, we use kind of corrugated geometry. By using corrugated geometry, we will be able to increase heat transfer area and consequently increase the heat transfer rate. Our second innovation is kind of a corrugated geometry. Chromatic geometry would enable us to perform self-supporting without need of a triangular air guide, because if it's a flat plate heat exchanger, you need a triangular guide, which cause higher airflow resistance. If we use kind of corrugated geometry, you can ignore the triangular air guide, you can reduce airflow resistance by around 15%. This is second innovation. And the third innovation is heat change seat. Because of this kind of dew point cooling or indirect evap cooling, its heat change seat would be kind of double layer dry surface, a wet surface. On the wet surface, it would be kind of fiber material. This kind of material can hold water and distribute water and evaporate water. So for this kind of wet surface material, we test more than 10 different material. What we expect to is kind of material which have a good water absorptivity, good water diffusivity, and fast moisture evaporation effect. And more importantly, this kind of material have a good binding effect with dry side material. Two material binding together with little bubble and little air gap. In that case, you can achieve significantly enhanced performance. We test the material and then we try to sort off the kind of material which performs very well in terms of moisture capture and evaporation as well as heat transfer. Lastly, but most importantly, we try to use kind of an intermittent operation of the water pump, because we don't want to create kind of waterfall or kind of water film on the wet surface. Instead, we only want to keep wet surface in saturated state. So without water film, without waterfall. In that case, we don't need the water pump to be in operation continuously. Instead, we can run intermittent operational scheme. For example, every half hours, we only need 5 minutes to keep pump on, and the rest of time, water pump will be closed. That is a strategy. In that way, we can prevent kind of waterfall and water film on the wet surface, or we need try to keep wet surface in saturated state, and in that way we would be maximize moisture evaporation and maximize heat transfer and maximize cooling effectiveness of the system. So here is comparison of the different binding technology. You can see we got three binding. The first group of binding is fiber only. We have nothing to binding. Second group is fiber plus aluminum plus adhesive glue, because the two kind of material bind together use kind of adhesive glue. And the third kind of binding material, we use fiber and aluminum. These two material bind together use kind of technology we call thermally assisted pressure technology without glue. You can see the evaporation rate of the third binding technology is much higher than the glue-based heat change rate, and the evaporation time would be significantly reduced compared to glue-based binding technology. So we made a dedicated heat change assembly. We make a kind of a dedicated watt distributor as well as control element, try to put them together, make an integrated unit like this. We implement various measurement sensor, temperature, pressure, and also flow rate, whatever, everything integrated into unit. We measure the performance of the cooler, and this is a measurement result. This is a measurement result at different climatic condition. Because this is a dew point cooler, is kind of indirect evaporate cooler. Its performance is largely dependent on its climatic condition. We selected 6 different climatic conditions, namely Florida, Riyadh, Los Angeles, Kars, London, and Beijing. You can say in American Florida condition, we can achieve COP of 37.4. Its temperature reduction level could be 17.10. Its cooling capacity could be 4.2 kilowatt. Of course, at different climatic condition, you got different output and different performance. And this is the nature of the evaporative cooler. So we also found working air ratio, which is working air against the total inlet air, somehow affect the performance of the system. At working air ratio of 36.4%, we would be able to achieve highest temperature reduction, which is 19.1. Its cooling capacity could be as high as 4.75 kilowatt. This is something we can achieve with optimal working air ratio. So we made a parallel comparison between our unit against the traditional Florida commercial unit M30. You can say in terms of the temperature reduction potential, our unit can achieve a temperature reduction of 19 degrees Celsius, which is at the working air ratio of 36.4. A traditional M30, it got temperature reduction level of 16.3. In terms of weight bulb effectiveness, we achieve a value of 113.8, and commercial product got weight bulb effectiveness of 19.3. In terms of COP, which is a significant increase, we achieve COP of 15.5. A commercial unit have a COP of 18.4. We almost triple this kind of figure. This significant increase is because of reduced pump power and reduce the fan power because reduce the flow resistance and the intermittent water supply can significantly reduce the power consumption of the system. In that way, you can significantly increase the COP energy efficiency of the cooler. So we made the parallel comparison between three kinds of cooler. First, traditional mechanical vapor compression cooler. Secondly, chloride dew point cooler and our cooler. For 4 kilowatt cooling output, traditional mechanical vapor compression cooler need power input of 1,315 watt. Chloride unit need power input of 215 watt, where our unit only need 19 watt power input, which we can say is a super performance, extremely low energy consuming cooler. That is a significant difference between our unit and the traditional coolers markedly available. So we address a number of scientific challenges in our research. First of all, you need a very high performance wet side material, which can firmly hold water on its surface, got good moisture absorptivity, good moisture diffusivity, and a good moisture evaporation effectiveness. Secondly, you need to determine water flow rate and film thickness. Best effect is in saturated state. In that case, you can maximize moisture evaporation, maximize cooling effectiveness. If you create kind of waterfall that would somehow resist the moisture evaporation and the heat transfer. And third point, you need to find a way to binding dry side material and wet side material. Our research found kind of binding technology, which is called thermally assisted pressure approach, can help achieve this kind of binding effectiveness between dry side material and wet side material. Another issue is heat and mass transfer, because you got fiber material, which is a porous structure. Heat and mass transfer across the porous surface is critically important. We need to look at carefully. And finally, we need to look at air and water flow in the dry channel and wet channel. Ideally, we expect water will be flow across the surface and air would flow across the gap channel, but real world situation would be much different. In the wet channel, water and air would be in a fully mixed situation. You got water droplet that would flow across the channel or in the full mixed state with air. That kind of situation will somehow reduce moisture evaporation, reduce the evaporation effectiveness, and reduce heat transfer, which you need to look at it carefully, use aerodynamic theory and laser camera monitor. That is a key issue in our research. Currently, we are working on an EPSC project, which combine dew point cooler with natural light-driven dehumidification together, make it near zero carbon and all climatic adaptive air conditioning. Because the dew point cooler is kind of a climatic dependent. At humid climatic condition, you would get very poor performance. By use kind of a dehumidification technology, we call light-driven dehumidification technology. We would be able to dehumidify the air pre to into dew point cooler. In that way, you would create kind of all climatic adaptive and net zero carbon air conditioning system. This system we use kind of sorbent and desorbent bed, which comprise two layers. One layer is a sorbent layer, another layer is a desorbent layer. Sorbent layer is used to absorb moisture from the incoming air, and the absorbed moisture would be transmitted from a sorbent layer to desorbent layer, which is through joint action between gravity, pressure difference, and concentration difference. In this joint effort, moisture would be transmitted quickly from sorbent layer to desorbent layer. On the surface of the desorbent layer, you got kind of natural light. We try to collect the natural light, striking onto its surface, which help moisture to evaporate quickly, and evaporated moisture would be quickly taken away and discharged to atmosphere. By combining dedicated dehumidification technology with the dew point cooling technology, we would be able to create kind of net zero air conditioner, which is applicable to any kind of climatic condition. Currently, we are working hardly on this kind of dehumidification technology. We hope we can come up with some more result, because we try to look at the material issue as well as how to combine the material with the light system. That is the work we are currently doing now. So that's it. So that's everything. Thank you.
Thank you very much for the presentation. As Patrick mentioned on the chat, fantastic innovations, a lot of innovation, single presentation. So thank you very much. Honestly inspiring. I'll open the floor for any questions. If anyone has any questions that they would like to ask, we'll take a couple because I know time is. Oh, I can see it, someone typing on the message. So I've got a question. So for the integration between for the integration between the heat pump, the tank, and the solar, what was the performance like? For example, in one of China's case studies against the UK, because obviously two different climatic conditions. What did you see in terms of the differences under those two contexts?
Yeah, you got a very good question. Actually, it's a quite different situation at different climatic condition. In China, you got very rich amount of solar source. So during the daytime, you almost have no need to switch or heat pump. So solar panel itself can provide heating for 8 hours or even more. And because we got kind of heat storage technology, which can store some amount of heat. So even during the evening, for example, 8 o'clock, 9 o'clock, 10 o'clock, even 12 o'clock, we can still use kind of solar heat. But in the UK, it's a totally different story because very poor solar resource. So during daytime, solar panel is not enough to provide heating. In that case, majority of time you need a switch or heat pump. That's why we are not going to use a thermal panel in a whole city council house, because we found solar panel almost useless in winter because of the poor heat collection and significant heat loss in the UK climatic condition. Yeah, this is the situation because UK solar resource is quite poor. So,
No.
but in China is a total different story.
Yeah. No, that makes clear sense. That makes clear
Yes.
sense. Thank you very much. Thank
Thank
you.
you.
We've got questions from so Mohammed's got his hand up, so I'll let you go first and I'll read the message on the chat.
Thank you a lot. Really amazing informations. Just I want to go back with you to slide 10, if I am not slide 10 or 11, where you show
slide 10, 11, yes.
Yeah, where you show the system of double evaporative. Where you show the system. No, go forward. The system. We'll show the system of double evaporative. We miss the temperature.
You
On the
mean
slide,
is this slide?
I think yes. There are one slide where we show the schematic with the temperature in the schematic itself. The temperature came in the end of the slide. We didn't see. Can you go forward a little bit? It is not this one. I think it is still. Yeah, this one. Well, back. One slide back.
Because we got two evaporator, which
not this one.
perform
The previous one.
previous one. This one.
Not. Yes. Yeah.
Because you got the evaporate 1, evaporate 2, which perform heat recovery. Two-stage heat recovery. You got more heat collected. You got more temperature reduction from exhaust air. So that's why we can collect more heat from ambient air as well as from the exhaust air. So you got
so the exhaust air is 20 degree, and
exhaust air is first stage heat recovery. After that, you got exhaust air mixed up with fresh air. Then you enter into the second evaporator, where second stage heat recovery
go to
will be
-7
performed. In that case, you got more heat recovered, and you got a more temperature reduction.
Clear.
Yeah, you can say the temperature reduction is much higher than the single stage heat recovery. You got the heat recovery rate is higher than the single evaporator because double stage heat recovery.
Clear. Thank you a lot. Thank you.
Yeah, thank you.
You are on mute, Mazen, Dr. Amr.
Oh, sorry. Thank you very much. So Patrick has asked on the chat is how many seasons worth of data have you acquired for the whole council house, and what are the key lessons learned from this?
For the whole council house, we test the system for 1 year, but measurement date only 1 month, 2 months. But because we found this kind of heat pump, it is used in the residential house. It got a little bit higher noise. Currently, we try to resolve the problem noise. So, but it's been running for 1 year. But we try to say, how can we reduce the noise? Because if you install heat pump in the residential house, noise is an issue, big issue, especially during night where people are in sleeping. So you need to keep very low noise. That is the issue we are currently doing now.
Brilliant. Thank you very much.
We have a 2 months measurement date. Yeah.
Perfect. Thank you. I can see a hand up. I think it's Abdul Rahman. Please ask your question.
First, thank you so much for your kind presentation concerning these innovations. As understood from your slides here, you can refer to the innovation dew point innovations. Yeah.
Okay.
Yes, as understood, this innovation for cooling the air, intake air, to generate and to accumulate the moisture.
Yeah.
Am I right?
Yes, correct.
Yeah. So as my background and my experience, we are working for this compressed air generation or compressed air station to control or to capture the moisture on the intake air for the some plant like cryogenic air separation.
Yes.
So I'm asking here, can we generate this moisture to become in a state of water? This is my question, because I heard some application, some companies here advertise produce cooler without water. This water from the air.
Yeah,
you need,
we have some technology to collect water and from air. We need kind of vacuum pump and try to separate moisture from the exhaust air. Use kind of water air pump. It's kind of water air pump. This is a new patent we recently submitted, which we try to capture the water from the collected air and have this kind of water condensed in the tank. This is a kind of compression pump which can extract both air and water from the channel. This is something we are currently doing. Yeah, we need the kind of vacuum treatment. We need to create a half vacuum, maybe not 100% vacuum, but at least 2,000, 3,000 Pascal at the vacuum chamber. Otherwise, you would not be able to recover this kind of moisture. You would not be able to create a pressure difference between supply air side and exhaust air side. You have to create kind of pressure difference. So we call it partly evacuated chamber.
So that means we cannot this technology. We cannot apply this innovation for within atmospheric pressure. This is
for humid climatic condition, you need the dehumidification treatment before it is delivered into dew point cooler, because the moisture is the hurdle for this kind of dew point application. You have to dehumidify air first, then you got dehumidified air delivered into the dew point cooler. You need kind of dehumidification treatment.
Thank you.
Thank you.
Thank you.
Thank you very much. I don't see any more questions coming in. So thank you very much, Professor Zhao, for your time. I honestly really enjoyed this presentation with the innovation. So thanks once more for your time. And thank you guys for attending, and I hope you managed to benefit. The presentation, I've recorded it, so I'll upload it on YouTube and share the link if you want to revisit anytime. Yeah, thank you very much, Professor Zhao, for your time. I really appreciate it. Thank you very much.
Thank you for inviting me, and good to be with you. Thank you.
Thank you very much.
Bye.
Thank you.
Bye.
Thank you. Bye.
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 Thank you. Bye.